Welcome to our discussion on the 1939 Nobel Prize in Physics. This time goes to Ernest Lawrence, who, if you watched the movie Oppenheimer, you probably heard his name. Not, you may have seen his character. I believe he was portrayed in there. If not, his work was certainly discussed. He won the prize for the invention and development of the cyclotron and for the results obtained with it, especially with regard to artificial radioactive elements. So he did a couple things using a cyclotron that he invented. One of those involves uranium isotopes. And if you're wondering what those are, the 1938 award went to Fermi and actually discussed those at length. So I'll watch that video and I'll explain it. But one of the things he did with the cyclotron was he found a way to separate uranium isotopes from one another. And that was instrumental in the Manhattan Project moving forward. He also managed to use the cyclotron, as I also discussed in the Fermi video, to find ways to create new elements. So he actually filled in spots on the periodic table with things that had never been seen before. And in some cases, if they exist in nature at all, it's a very trace element level. So let's dive right in and look at Ernest Lawrence, a fantastic scientist who was way ahead of his time. Okay, what is a cyclotron? If you watched the movie Oppenheimer, you heard the name a couple of times, you saw one in a lab. But what the heck really is that thing? Well, it's a particle accelerator. It takes small particles, charged particles, and accelerates them so that they can move outward from the center of a flat cylindrical vacuum chamber along a spiral path. Particles are held in that spiral trajectory by a static magnetic field and accelerated by a rapidly varying electric field. Before this, accelerators were largely electrostatic. There were a couple different types, the Calcraft-Walton, the Van de Graaff generators, a couple different ones. But no matter what type of accelerator they are, they're all designed for one thing: to speed particles up and smash them into each other or smash them into a target. As that process of those collisions actually unlocks new information, which is a whole video in and of itself. And someday I will do that video, but it's not going to be as part of one of the Nobel Prizes. It will be its own separate standalone thing. But for the moment, just understand that they make little charged particles go really fast and smack into other charged particles. Now, why do we care? Well, they've been used for a lot of things over the years. This is actually Lawrence's 60-inch cyclotron that he was responsible for building at the Berkeley Radiation Lab. The two people you see in the picture are Glenn Seaborg on the left and Ed McMillan on the right. They used this very cyclotron to discover, among other things, plutonium. Now, there's other things besides transuranic and bomb-making material you can do with these things, but now, why do particle accelerators matter? Well, they help us understand these subatomic particles, things smaller than protons, smaller than neutrons, and they really help us understand the forces that shape them and hold them together and how to create these new elements. That's what these things are really good at. Those particles have been used in a lot of different things, including medical PET scanners. Those types of materials are produced with accelerators. New generations of airport scanners post 9/11 are based on some of the same technology. MRI scanners, in some ways, owe their existence to acceleration technology. And even new medications that are being developed every day owe their origination to particle accelerators. They're used for a great many things. Cyclotrons aren't necessarily used as often as they once were. They were a great design for their time, but things have come a long way. Now, how far have they come? Let's take a look. So the reason Lawrence's 60-inch cyclotron was so important is that the larger that ring, the bigger around that ring is, the more circumference you get for the charged particle, the higher an energy level you get it to, the kind of faster you can get it going if you think about it that way. So in its day, Lawrence's 60-inch machine was fantastic. It was great. They learned things that they could never have learned any other way. But to get things to those higher energy levels to learn even more, you have to go larger. Well, the largest one in the world is now the Large Hadron Collider, which is 17 miles in circumference. This thing is huge. It allows you to get to energy levels that were just unheard of in Lawrence's day, but I'm sure he would have loved to have been able to see. Now, what else might the Large Hadron Collider and any accelerators that are built from this point on tell us? Well, all kinds of things. One of the things the LHC may be able to explain or help us figure out is, how do you really bridge that gap in between quantum mechanics and Einstein's theory of relativity? those there's a gap in between those two that's still not completely understood, and what secrets might lie there. And that's one of the huge things that these types of facilities might be able to help us understand, along with, are there really other dimensions? We see it in sci-fi movies, we hear about it, but are there really other dimensions out there, and can we get to them? Now, why is gravity so weak compared to the other fundamental forces? And it is very weak compared to like the electrostatic force and others, the nuclear force especially. But why is that? And the Large Hadron Collider might be the pathway to get us there, to understand those fundamental things in nature. And I hope it happens inside my lifetime, because it would be truly, truly exciting. So that's Lawrence. He really was, one of the greats. Certainly deserved the prize in 1939. We'll see you on the 1940 prize, and don't forget to click subscribe and like on the channel. Thank you very much. We'll see you on the next one.